record. All right. Good morning to you, Joe. I'm sure you can hear me. This lecture is on map projection and georeferencing. Is that okay? Map projection and georeferencing. So, what is it about? The reason I'm showing you that Google Earth image is because the Earth is round. So I'm going to go back and show you the Google Earth image again. Okay, the Earth is round. You see, we always talk about the Earth being round, and you know, children are not really. I don't know if it's in their curricula. They didn't even talk about it. We see the Earth to be flat, but this is how it looks like from the sky, way up. Are you all right? So, how do we represent such a round thing on a flat paper? You know, as even a builder, you realize that all your plans are flat, Andy. Meanwhile,
Yes,
you are building on something that is round. You see how interesting it is? So if we were to stick a building on this round thing,
hello.
you can see that your drawings have a problem, isn't it? Because when you draw
Yes, sir.
the foundation line is straight. So
Yes, sir.
when we get closer to the earth, we don't experience the spherical nature, how round it is. Are you okay? When we get down, deep down into Ghana, you can see that we forget. It's not that we forget, but at that large scale, you don't appreciate the earth being round anymore. You feel it's flat, but it's actually what? Round.
Can I record?
You can record. I'm also recording, so I can allow you to record. Yes,
Okay,
so
sir.
I will allow you to record. Just let me allow you. So allow record. Okay, so you can record on your own. Is that okay? But I'm also recording. I've got this for YouTube. I'm getting this for YouTube. Yeah. So
Okay.
as you can see on top, that could be your building in there. Are you okay? Somewhere.
Yes.
And it's interesting how you are just living and walking around here, thinking that you are really like on a flat surface. If you tell people, there was a time where if you told people that the world is round, they will actually fight you. They're going to go like, no, you are lying, it is not round, but it is flat. Are you okay? And
Sir.
there was a discussion between the king of Spain and Columbus, who was some kind of explorer. And then Columbus was saying that, hey, king of Spain, I tell you that the earth is what? It's round. And the king of Spain will say that it is flat. Okay, then you say it is round, and then you get again and say that it is flat. It says that it is round as an apple, and then Columbus will say that it is okay. Columbus will say it's round as an apple, and then the king of Spain will say it is flat as a pancake. Okay, but what I'm telling you now is actually coming from a cartoon. Can you imagine that? It's a cartoon that showed it. But the truth is that people have been killed because they say that the earth is round. And I'm sure some religions don't even support the whole idea.
Yeah.
You're supposed to even talk about it. It's like the earth is there and the moon is there. But yes, it's good. I'm sure God has given us this knowledge. Our lecture is trying to talk about how to represent something round on something that is flat. Because if you are putting something round on something that is flat, then I think we have an issue, don't we? Because it will not really fit it.
Yes.
So the concept of representing the round earth on a flat sheet of paper is called map projections. Are you okay? It's called map projections. So we want to look at map projections and then georeferencing. And what is georeferencing? Georeferencing is just saying that find a way to tell me where you are on the Earth surface. So whilst you talk about map projections, one, we are linking it with position where we can find ourselves. Are you okay? On that round thing. And we all know that one of the easiest ways to represent ourselves on the earth is through what we call the longitude and the latitude. Okay, So longitudes and latitudes are these lines that go from the north to south and, you know, left, east to the west. Are you okay? That define where you are. When you watch Prison Break, coordinates, people were being killed because of two numbers, coordinates, you know, which later on they found out that it was really a building blueprint. It was a plan to show where something was hidden. You know, I'm still watching Prison Break. Anyway, I'm learning a lot from Prison Break even still. So you're referencing map projections, the basics. I want to teach you the basics and then we go. Is that okay? We have just 30 minutes or so, maybe 15 minutes, but I'll try to be as fast as I can. So follow me. One of the things we need to know is that we are representing something very large on something that is very small. If you've actually gone to the seashore before, you look at the sea, look at how big it is. In fact, you see that it's enormous. It engulfs you. Representing even a large building project on a sheet of paper in itself, the word scale comes to being, that you need to scale it. We need to reduce it, the measurements in the real world, into something that we can represent on a sheet of paper. So there's a small formula here for you. I know construction students, you don't like a lot of formulas. I don't know. Am I right or am I right? But then, yeah, this is a very simple one here. So scale is the distance on a map. So the map is a sheet of paper, okay, over the distance on ground. All right, so that is scale. Very simple, isn't it? So instead of saying map, you can say plan. So let's not let the word map scare us. The map is just something big. I say the map of Ghana. But then plan of a building, you realize that the building is very small. Ghana is very big and very large. So map scale, as you can see from the top, is the method for expressing how map distance compares to ground distance or the distance on the surface of the earth. Very simple. Are you okay? All right. So we need to know that. Now we have different ways of representing scale on a map. Are you okay? We have what we call the graphic scale. So this one is a graphic scale or a scale bar. So when I put this on a map, you can see that here we have 440. That means that when we measure from here to here, it's 440 meters. But Joe, you agree with me that from here to here is not 440 meters, right? From here to here is just a few centimeters, maybe 4 centimeters. Are you okay? All right. So the scale, you know, can be represented using graphical elements, like something like this, you know, with black a bar. Are you okay? And then we put the actual distances on it. The scale can also be represented as a fraction. So as you can see, 1:2,500. I think construction students should be used to this one. Are you okay? 1:2,500. And that means that every measurement I make on the paper is actually 2,500 times what I'm actually measuring. So if I measure 1 millimeter, that means 1 millimeter, I'm actually measuring 2,500 millimeters. I think we should know this. I'm sure Joey knows this. Yeah. So we need to know this as we try to represent the large round earth on the flat surface. Large scale versus small scale. So I think I should have asked you first before I put this one there. Why is 1,2,500 larger than 1,200,000? I think if you show this to any little child, they'll tell you that, uncle, you are lying. This one is bigger than that. So why this is bigger than this is because if more, let's divide. It's something that was taught in primary school. You know, I went to Saito and they didn't they didn't teach us that one. You know, they only taught us to play a lot and to be jumping around. Yeah, no, sorry about that, but obviously not everybody learned that. 1/2,500, because 2,500 is smaller, the result of this division is large. So if you have one thing and you want to divide it by 5, compared to 1 divided by 2, I would like 2 people to share one thing than 5 people. I mean, this is sounding like primary school maths, but I'm telling you that this beats a lot of people because they're not referencing this. knowledge. All right, a smaller scale number means a large scale number means smaller scale. That is what we are saying. All right, so map projection concepts, round earth to flat surface. Are you okay? So we see this a lot, world map, this one. We see it a lot. And every time that we see this, I mean, we all thinking, okay, world map, everybody just singing that song. It's a mantra, world map. But what we're not asking ourselves is that it's actually something round that has been split up to become flat. Okay?
Yes,
Except that these days, when you watch TV, CNN, BBC, Joy News, they are all showing us this round one. Then they try to zoom in, and then we begin to see a close-up of that. All right? Now, we cannot actually analyze data if we don't have a conversion from the round thing, which is the sphere, to the flat surface. So between the sphere and the flat surface, we have longitude and latitude. Okay, so longitudes are represented here, latitudes over there, and then we can have XY coordinates on this end. Okay, so X, Y coordinates. What does this mean? I'm sure you are wondering, what am I talking about? Here we have a grid. Okay, we have a grid over here. These straight lines you see here are representing the longitudes. Then the ones that are going from left to right are the latitudes. So we are but on this one, on the globe, these same lines do appear, but they all don't go to a flat top like a straight line here. They all go to what we call the North Pole. Are you okay? They all go to the North Pole. So the North Pole is around this area. Okay. The South Pole is around this bottom bit, and then the North Pole is up here. Okay, and then we are drawing lines to actually join up the top to the bottom. So we're going all the way. Okay. So I mean, I'm not doing it well, but obviously you can see that we are actually converting curved lines into perpendicular and orthogonal lines. Okay, what is perpendicular? You understand perpendicular lines? Lines are metered 90 degrees. So another word for that is orthogonal. Is that okay? So you are in a university, so you see we are introducing very scary words here. Orthogonal or orthogonal. All right, so that principle, that whole idea of mathematically doing a conversion between two variables or two sets of variables, longitude and latitude, to XY coordinate is what we are calling map projection. So map projection is mathematical. Are you okay? All right.
Yes, sir.
Okay. So why do we do map projection? One of the reasons is that we need to integrate data. We need to bring one data set and join it to another one, so that if you are working on a construction site and I want to know, okay, some people have been affected by COVID and we saw them running around and we put GPS on them, and the GPS has given us some coordinates. All right, okay, where's your building? Oh, your building is at this place. Okay, the GPS coordinate now need to be reconciled with your building project, so that we will know exactly where the person is. Maybe he's gone to where your construction site is. Are you okay? So that we can implement some security measures at the construction site. So map projection concepts are necessary because we need to integrate data sets into our GIS. We need to integrate. Integration means bring together. All right, any questions so far? So everything you see here is just repeating what I'm talking about. Is that okay? We are dealing with three-dimensional coordinates. Are you okay? And the three-dimensional coordinates are X, Y, and Z. X, Y, and Z. Okay? And it's convenient surface to deal with as opposed to three-dimensional. What are we actually saying? What we are actually saying is that when you have the sphere or the round surface, that is what we can relate to, exactly the globe, really. Are you okay? But then when we actually do the transformation, then we want to easily work on it. You can easily work on a flat surface. as compared to a round surface. You can easily work with a flat sheet of paper as opposed to a ball. Are you okay? So as a construction guy, how would you feel if the whole world was reduced into a round surface and then we needed to actually, oh, Joe says you can't hear me. What happened? Okay, so let me just revisit what happened. Manage my participants. Joe, can you hear me? Joe, can you hear me now? What happened? Just lost the sound. Wow. Okay, kindly rejoin. Kindly rejoin again. Let's see. I'm waiting for you, Joe. Just go off and join again and let's see. Can I pause this recording and on this computer? Can we pause it? Sure. Okay. Joe, kindly rejoin. That means go off and come back again. All right, so let's wait for Joe. Recognizing that I'm making this video for YouTube, and whilst my participant rejoin, I need to still repeat some of the things that I said about map projections, that they are really mathematical relationships between longitudes, latitudes, and then a Cartesian coordinate system. You know, it's like straight lines, curved lines, try to relate them. Yeah, Prince. Morning, Prince. Prince, hurry up. I'm doing a lecture, so hurry up. I'm listening to you. Are you joining? Or he's sick? Okay, Joe is back. Joe is back. All right. Joe, are you okay? Can you hear me now?
Yeah, I can hear you now, sir.
Hey, so what is happening, cry? Hey, anyway, did you pray this morning? Okay, don't mind me. Joe, let's carry on from where we left off. So I was saying that, or I want to reiterate or repeat that map projection is just a relationship between longitude, straight lines, perpendicular lines, straight perpendicular lines, and then curved lines. But the curved lines are on a globe. Are you okay? And the straight line. These are the principles that you are being taught today, this morning. All right. So let me just show you. So mathematically, let me just give you a little bit of maths here to make you feel good. Okay.
Sir, I want to record, so.
Yeah, go ahead. Have I stopped you from? Go ahead. Should I allow you to record, right?
Yeah, allow. Yeah.
Okay, hold on. All right, so you can record now. I think I'm also recording. If I'm, yeah, recording. All right, great. So carry on and moving forward. One way to think of a map projection, therefore, is that it transforms the position on the Earth's surface identified by latitude and longitude to what? What does it transform it to? Cartesian coordinates.
Cartesian coordinates. Okay.
Yes, X and Y. Are you okay? So
Yes, sir.
the latitude and longitude are curved lines. You've heard about this before, I'm sure.
Yes, sir.
And they run from the North Pole to the South Pole. Is all right. So when you go, if I share my Google Earth again, you will see that I can show you the grid. Okay, so you can see these straight lines are moving from the top here, okay,
Yes.
to the bottom here. All right, people have been here. Can you believe that? People have been to that bottom all the way. It's interesting, isn't it? Yeah, but
Exactly.
the whole idea is that the straight lines moving down, they are trying to help us to find a place. So for example, if I want to know where I am somewhere in here, then I need the so-called coordinates. Are you okay? So let's assume that the coordinates, if someone is here somewhere, where I've put this yellow thing, okay, someone is also at C. Okay, so see the yellow thing,
Yes.
the star that I've put there. Where am I? If someone is here and they are missing, where is the person? We need to now find this yellow line and say that, okay, it's the equator, it's called the equator. Actually, this is a 0 latitude. Are you okay? And then
Yes,
we
sir.
need to now figure out which one this one is. And you see that that's between 10 and 5. So that's say 8 or 7.5. Are you okay?
Yes,
And
sir.
so that it means the person is at 0, 7.5. So if we travel down, like we are now on a grid. Are you okay?
Yes, sir.
One of the
I
people
get
have discovered that this is one of the easiest ways to find something is to grid the place. So in construction, I know that you grid,
it. Yes.
right? So
Okay.
that you will know where things are and which areas you are working. Okay, so that is the whole idea of longitudes. So these vertical lines are longitudes. Vertical, but they are curved. You can see clearly that they are curved. All right. And you can see the numbers are actually varying from what? 0, which is the longitude. 0 goes through Tema. So this is Tema. Are you
Yes.
okay? The reason why we have, you see Tema is coming up here. All
Yeah.
right. So this is called the Greenwich Meridian. And it's called Greenwich Meridian because it's actually going through a town called Greenwich in England. Are you okay?
Okay.
So if you actually trace this all the way up here, you can see that we are coming to United Kingdom and there's a place called Greenwich. That is where this line is being monitored. So it's actually a physical thing. Are you okay? But the one here is only imaginary.
Yeah.
So Greenwich is somewhere in London, somewhere in there. Okay, so obviously it's not easy to find it at the moment, but yes, if you really, really, yeah, search for it, you find it like somewhere along here. All right, so that is what longitudes are about, okay, and they are values. Are you okay? Longitudes
Okay.
are actual values. So going back to the lecture, when did I get to this point? Where's my mouse? Okay, so back to that. So the longitudes are these values, and then the XY coordinates are what we have. When you buy a piece of land, you see that the surveyor will be writing values for the piece of land. Are you okay? He will not be writing
Yes.
the longitude large, he'll be writing this one. So at that
Yeah.
point, XY coordinates, yes. So the map projection is trying to say that don't lie to yourself. Your actual position is this one. But then I need to convert you to something that is convenient. Are you okay? So for convenience, we do that. So this is the mathematical relationship between the longitude and the XY. Okay, so this symbol is called lambda. This is called phi. It's a Greek symbol. And pi is actually a value, 3.14 something something. All right, and these are trigonometric functions that allow us to convert longitude to latitude. This particular transformation is actually the transverse Mercator transformation, and it's being called that because the person who created it, are you okay? It's called
Okay.
Mercator. Let me put that way, and we are naming after that. So we can actually convert flat surfaces to round surfaces and round surfaces back to flat surfaces. So this first set of equations say that convert longitude and latitude, round surface to flat surface. And then the second one down here is actually saying that what? I want to convert from flat surface to round surface. So take an orange, for example. When you peel an orange and you decide that, okay, I'm going to peel it in such a way that when I finish, it won't be apart. Are you okay? That you have that type of thing happening here. All right. If you have a question, you can ask as we go. All right. Now, what happens with this thing is that the whole thing is round and you're trying to make it flat. So you're going to have what we call a distortion. And a distortion is a distortion. A distortion means there's something not correct about it. Are you okay? So the distortion created is as a result of you trying to put something around or convert something around on some, or putting something around on something that is flat, stretching it. You end up all areas which are very small some become large. Smaller areas can get expanded and all that. So we can have distortion in your areas. So the question is that when a pilot is flying from Kotoka to, say, New York, are you all right? What kind of map does he use? Because the map that he's using is distorted. Are you okay? So, I mean, I don't want to take you deeper, but you think about it. That if that map is not really close to the globe, then it means that he's getting a distorted, map. What he's holding is not really, is having some distortion on it. Okay. So people came out with different ways of making a map, because someone will say, oh, the way you've done it, there will be so much distortion. Are you okay? Your idea of how to really represent the round Earth on a flat surface is going to cause problems. In fact, we have had ships sink in the deep sea, traveling from one place to the other in the past, simply because the coordinates were not right. You think about it. You're talking about distortion here. Are you okay? Talking about coordinates not being correct. And etc. I don't want to get emotional about it. It makes me talk too much about the same thing. All right. So we have different types of what? Projections. Is that okay?
Yes,
Different types of projections. All right. So let's move on. All right. So where are we now? Data sources for maps come in different projections depending on which characteristic. Okay. Okay. Great. So maps can come in different forms. All right. I want to just get rid of this. Clear all drawings. Okay. So we need to decide on which map we are holding. We can have what we call equal area maps, IOC equivalent map. There are different types. In fact, some maps are so wrong. In fact, the people claim that the US is not as big as we say it is. Why? If you go back to the globe again, you realize that, yes, which part of the earth do you think really, if you represented it on a flat surface, you see that US is really not. Look at Africa. Africa is, all the areas that we are calling Abuchi, Europe and blah, 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 all this COVID thing we are spreading out there is just a small part of something. Are you getting that? The top part of the thing. Hey, so it's not as big as you think. But once you spread it out into a, what do you call it? A flat surface, then you have an issue. I'm talking about Google Earth, Google Map here. So I'm going to also show you Google Map. Is that okay? And you see that Google Map, now they are trying to make it round as you zoom in, but this is supposed to be, at first you had it flat. I think now they've made that one too round. So as I zoom in, the Earth should remain flat if they haven't turned it around. So now here is the world. And you see the deception between this one and then this one.
Yeah.
I'm coughing a bit, but I'm fine. Is that okay? All right. So after talking for a while, you get a dry throat. You can see clearly that something that is round and something that is flat are not the same. Yeah? Okay, so there's that little deception with map projection that we should all be aware of. So children can be shown a certain map that will make them feel inferior and feel like, okay, we are Africans, we are very small. Okay, depending on the type of map that you show them.
Yeah.
All right. Okay, so let's move on. So we need to decide on which way. Now look at this one. Can you see these diagrams here?
Yes.
So people were coming out with ideas. Okay, so how should we represent the what? The Earth. How should we go about representing the round Earth? So this is the Earth. And someone said use a cylinder and then stretch the Earth onto it, project it onto it, open it up, cylindrical projection. Someone said use a cone, put it on top of the Earth, project the longitudes and latitudes onto it, and then stretch it out, cut it up. You get something like farm milk. Do you remember farm? You still know, you know farm milk. Their symbol looks like that, isn't it?
Yeah.
Then someone said, no, put a flat surface on top of it, and then project the longitudes onto it. And then once you've done that, that's the best. Then someone said, no. Really, all of them can work. It depends on how you actually look at it. For example, the cylindrical one works very well in the tropical area, Africa. Are you okay? Brazil, Southern America. Are you okay? All right.
Yeah.
Now, the conical one works very well with the temperate regions. Are you okay? UK, Asia. Are you okay? All right.
So,
Now, and then we can talk about the azimuthal one. That's another name for that is also stereographic. Are you okay? The stereographic, azimuthal, flat surface, conical. They are all good, but this one, the azimuthal, the flat one is good for the polar regions because you see at the poles, the Earth flattens. The Earth is a bit flat at the poles. It bulges. Are you okay? The Earth is like, the top here is really like flat. Are you okay? All right. So it's very important for it to know that you can see that people don't leave yellow because it's very cold around here. It's very cold.
yeah.
All right. So let's go back to the lecture. Where are we? Okay. What are you seeing on your screen right now, Joe? What are you seeing?
I see the cylindrical, conical, and azimuthal.
Okay, so at the top you see developable surfaces, right?
Yeah.
Okay, great. So cylindrical, use a cylinder, conical, use a cone, azimuthal, use a flat surface. We call this the different classes of projection. All right. So yeah, the datum is simply the reference surface. On a construction site, you realize that there is a reference with which the whole building is being set up. There's a certain point that if you have a surveyor on site, he's always using that point to control the whole building, the setting out. Okay, so that's the idea of a datum. It's a reference surface. Is that right? So we can talk about the Earth itself is not spherical. It's not spherical. The Earth is like, some kind of pastry. Is that okay? There's a pastry called achumo. In local, she called it achumo. The Earth is like that. It's not because you have the mountains and are you okay? High places and low places. Are you okay? But then mathematically, we try to use something like called a spheroid. Just like a sphere, something round, like what I'm showing you in Google Earth is not how the Earth really looks like. It is more rough on the surface. It is more curvy at the surface. Is that all right? So we talk about the datum, define the position of the spheroid relative to the center of the Earth so that we can control our measurements. Are you okay? All right. So I think sometimes I take you a bit deeper than I'm supposed to. Let's move on. The datum provides a framework of reference for measuring locations on the Earth surface. Is that all right? All right. So the next thing that we want to look at is what we call the universal transverse Mercator. You need to ask questions. If you feel like I'm loading you need to ask questions. Are you following what I'm saying?
Yes, after this, I'll go through the video again, then I'll pick out the things.
Okay, so I should just carry on. Okay, so let me carry on then. All right, that's fine. So we come to the next topic, which is the universal transverse Mercator. And what's the universal transverse Mercator? Universal transverse Mercator is a coordinate system. It's a projected coordinate system which makes use of a cylinder. Are you okay? And the cylinder is wrapped around the Earth. Are you okay? Like in the case of what I showed you previously. The cylinder is wrapped around the Earth. That's on the left-hand side. Are you okay?
Yes, sir.
Yes. So this is the universal transverse Mercator. Why do you call it universal? Universal because it is that coordinate system covers the whole world. Anywhere you are, you can relate to it. Is that okay? All right. So I want to move on. Okay, yeah, going. The universal transverse Mercator, the distortion on it, in other words, when you represent something on the universal transverse Mercator, it gets distorted by a certain scale factor. So these numbers you are seeing here are saying that when you actually have a certain portion of the earth represented by that cylindrical shape, okay, that cylinder, cylindrical projection, then we have at the central meridian, CM here is representing central meridian. Are you okay? Central meridians. So this is 0.966 scale factor. If you say something has changed by a scale factor of 1, what does it mean, Joshua?
It means a scale factor of 1. It means that it has increased by.
So remember factor, that means you multiply. Are you okay? You multiply. So if something has changed by a scale factor of 1, if you weigh 55 kilograms and you have changed by a scale factor of 1, that means that 55 kilograms times 1 equal to 55, which means that you haven't changed. So scale factor of 1 means, so a scale of 1 means nothing changed. So a scale of 1 is to 100 means that everything has changed by 100. Everything has been multiplied by 100. So most of your construction elevation plans, yeah, is floor plans and all that are at a scale of what? 1 is to maybe 100, 1 is to 200, something like that, depending on how big it is. And so this scale factor here is telling you how much you're changing. So when you look closely at the number, it is close to 1. Look at it very carefully. It's very close to 1. 0.996 approximately 1, isn't it? 1.003 is approximately 1. You can take off this bit and you get 1. 0.9 close to 1. So it means that the distortions are, it tells you that it's not really like spot on like that. It was established, the universal transverse Mercator was established in 1936. In 1936. Are you okay? And then the coordinates used for the universal transverse Mercator are actually with reference to an origin. Are you okay? And the origin, can you hear me, Joe? The origin is given a false easting. Yes, the origin is given a false easting of 500,000 meters. In other words, when you are doing a graph from JHS, you remember that you are given a large values to plot. Then you have to assume that the origin, yeah, for your graph, the left corner is having maybe 200, 300, so that you can plot the values, because all the values are between say 200 and 300. The same way, we can have an origin of false easting. In other words, the easting is the longitude, and then the northern is the latitude. Are you okay? Later, I'll explain to you why easting is rather longitude, and the northern is rather what? Latitude. So northern means you are measuring this way, and if you are measuring from bottom up, then your latitude can do that job for you. So these are latitudes, these are longitudes. Are you okay? Or if you like, these are just all right. So moving forward, we have, I want to go to my next slide. Come on. Okay. You have advantages of using the system. It is frequently used. A lot of people are talking about UTM these days. So if you don't know it, it means like, you know, something is popular and you don't know it. Well, it's up to you. It's trending. Are you okay? Why? Because it's universal. Everywhere you go, people can relate. You don't need to do a whole lot of calculations. It is consistent for the globe. You can have anywhere you are. Are you okay? So it's good for the globe. It is universal approach to accurate georeferencing. So it's been accepted. The disadvantage is that you need to know, are you okay, where you are, where are you, am I in which zone? Normally use a zone. Ghana is in zone 31 north. Are you okay? Ghana is actually between 2 zones. 30, some part of Ghana is 30, some part is 31. Are you okay? So the earth is divided into strips like that. Okay, so you can assume that we are cutting from the North Pole to the South Pole, North Pole to South Pole, like that. 30, about so many of them. How many zones? We have 60 zones. Are you okay? about 60 zones, and every zone is about 6 degrees in width. Are you okay? So when you measure around the globe, you want to measure in terms of what? Degrees. All right, so rectangular grid superimposed on zones defined by meridians. Okay, so there are some problems that I think we all need to take note of in terms of the whole thing is trying to be, we are trying to divide the earth into squares, are you okay? Into regular rectangles. Meanwhile, the earth itself is not like that. It is like round. So we have issues. There is an issue of the mathematical relationship. It's not simple. You saw the equation that I put out there, right? So we don't have any simple mathematical relationship, okay, between the coordinates of the zone and the adjacent zone. Even the one I showed you is not zones, but you can imagine that if we were to show you, if I were to show you the zones and the equation, yes, you are going to have an issue. Okay, let's move on.
So Prince is online. He says you should let him in.
Okay, I'll let him in. I'll just go and let him in now. I don't see him there. He's saying he's there, but I can't see him. So maybe when he comes on, I'll add him. But you ask some questions. Ask any silly question you like, whilst you wait for him, so that he can join us. So you just ask any funny question. I know it's not easy to immediately grasp everything, but you just ask any question, so that we're waiting for Prince for his sake. I don't want to continue. I'm almost finishing anyway, but just so that he can feel like he was even part of this. Just a few seconds. Okay, then let me ask you questions. Let me ask you a question. So do you think that the earth is round? In your own opinion, do you think the earth is round? What makes you think the earth is round?
I think the earth is round, and I think in elementary school we did a few experiments on.
Okay.
Yes, that's when the ship is sailing on the sea.
Yes.
Yes, and you are at the shore. You see that when it's far away,
okay,
it kind of
disappears.
Yes, disappears, and when it's coming closer, it's like it's appearing.
Yeah.
So that's
In
one.
fact, that is a perfect example of. That's why I was saying to you that it's when you go to the sea shore or the coastal area, that is where you really appreciate like the enormous, how enormous the earth is. Are you okay? That one, it is large, and then two, you got to see itself. As you said, you see ships coming, all of a sudden they appear. Where did they come from? Why were they not seen afar? The so-called horizon, it's all an indicator of the fact that the earth is round. Also, one of the reasons to know is the repetition of morning, evening, every day you have morning, evening. Yes. Telling you that. Yeah.
And it's like I joined meeting again.
Yeah, try and join again. Hey. Tell him to join again. A lecture that's almost over. You're not trying to join. I think Prince didn't even make the effort at all. He didn't. He's gone to do something and he's not trying to. It's easy. I think this is the first time we are doing this, Joshua.
Okay, the last time I couldn't join and because of
so this is your first time.
This is my first time. So
he has no excuse. You see, once you are learning to become an engineer, builder, and everything, you should be disciplined. You have a lecture. You wait to the last minute. I don't want to turn this into like, castigating him and all this thing. All right. So I'm not seeing him here. I'm looking at it. I'm not seeing him. He's not trying to join. But yeah, as you said, there are so many signs. You can see that someone was also asking about, do we see the moon and the sun at the same time? During the day, can we see the moon? And someone was asking that. And I told him, yes. If you look out for it, you will. But because the sun is there, our attention is on the sun. And we don't realize that the moon is also there. But in the night, the sun is gone. So everybody thinks that it's time for the moon to shine. Are you okay?
Yeah.
So these are very interesting things. It only tells you that God is great, who created the earth, in the moon, and He's done it perfectly. And why don't we fall off the earth if it's round? These are questions that children always ask, isn't it? If it's round, then why are we not coming off? Someone in construction asked that question in a class a couple of years ago. So I say, why is that people don't follow? If I want to give them the answer, everybody was just staring at me like I'm the one who created the earth. But I think we have tried to define what is happening. Are you okay? In terms of physics. Prince is going to waste our time. He can watch the video.
Some new another link be.
Well, he has to use the link to join. What else is he using?
Last link, just click on it. And then I'm catching some information. Okay.
It's so simple. You have been given a link to join a meeting. Click the link.
Let me give you the ID. My memo ID.
Okay, so whilst we are on this commercial break waiting for friends to join, I think we can all look at it again. For now, Google even have Google Sky, Google Earth have the sky. You can even look at the sky. Sky view. So let's look at. I don't even want to go into this, but you can see we are going to the moon. So yeah. So guess what? I don't want to, this is not part of the lecture, but because Prince is struggling to even join me. Do you see this? This is the moon. Can you see that? We see it from the, now we can see it. This is the moon. Interesting, isn't it?
Yeah.
Well, whether they are lying or not, we can't even defend it, but it's also round. It's beautiful. I'm using Google Earth to do that. Google Earth is just, and they say we can see Mars.
Yeah.
Mars and other planets. I don't know. So are they saying they have mapped it? We haven't been able to map Ghana, and yet we are mapping something outside the Earth. So that is how interesting the whole thing about studying and science is about. So Prince cannot join us. What do we do? Joshua, what is he saying his problem is?
Yeah, he's having problems with, he's not like the same problem I had from the beginning. I was trying to join with the link, but because I'm using a laptop, I'm using a laptop, so I need the ID and password. So it looks like I don't know whether he has a problem with entering the password.
Oh, okay.
So I just mentioned it to you. I think there are some caps and some which are lower caps. I think that's what he's having problems with.
Oh,
so
but I think he should, you see, we know what I'm doing. I've installed WhatsApp web. So when I want to copy something from WhatsApp, I copy it straight, I put it. That's why I'm able to put it there like that. Otherwise, I think you always have an issue. He's taking so long, and I think we are almost done. Let's carry on. We can't keep on waiting for him. If he joins us, fine. Let me run up. Is that okay?
Okay, sir.
Yeah, because we have 40 minutes, and I'm sure time will be up very soon. We have to. So let me run up. Actually, let me see how many slides I have to finish this one. Okay. So now I need to do a share of my PowerPoint. Okay. So yeah, you can see where we are. In fact, the next topic, so we need another lecture, which we can have maybe on Friday. Is that okay? But I think we've almost come to, we've come to, this was the last slide for the map projections. Okay.
Yeah.
there is something that I haven't talked about that I think will be in the excuse me, say the handouts. Is that okay?
Yes.
Which you never got, because my handouts, I'll be honest with you, I don't give the soft copy. I only give this hard copy. You know, so what I want to introduce you to is the tutorial. We are going to have a tutorial.
Okay.
So I'll send it to you. The school is trying to establish an e-learning portal. So when the portal is ready, I'll load some stuff there for you. Is that okay? Some materials out there for you. So that is that. I wanted to show you something more on the projections, because what you are seeing seem to lack something. Are you okay? What I've shown you so far. There's what we call the aspect of the projection. Oh yeah, okay, the class of the projection, and I wanted to show you those pictures. Class of map projection. I'm just trying to see if I can get you something on Google right now. So let me share this one. Okay. Quickly, I'm rounding up. The lecture is over. I'm just showing you extra things. Okay, so you can see that we have an explanation of when you tilt the cylinder. This cylinder here has been tilted to align with orthogonally with the axis of the Earth. So the Earth rotates around this in this direction. Are you okay? And we have the cylinder going in the opposite, perpendicular to that direction. Okay. So the Earth rotates around this line, and the cylinder is also going in this direction. Okay, so when you have this situation, we have we call it the transverse. Transverse cylindrical. Is that okay? All right. So we have this called the aspects. So we have three aspects. We have the oblique, transverse, and then we have the normal. The normal is what we have at the top here. Okay. So what we have up here, these are all normal. So normal cylindrical, normal conical, normal azimuthal. But then when we tilt this so that it is neither normal nor transverse, in between this normal and the transverse, we call it oblique. If you've done technical drawing before, you've met this word before. Yes. Yeah, oblique. Then we have what we call the secancy, and all that. Secancy means a cut. Are you okay? So here is cutting, etc. Are you okay? So you can see that here we have the cone is cutting through the Earth. But this is where we have Japan, Asia, China. They are all around this part of the Earth. That is why we want to talk about the conical projection for Asia. So I wanted to talk about that aspect. Is that okay? You can see that here, we are explaining what longitudes and latitudes are. The line moving from here to here. Okay, etc. Okay, then more equations. In fact, it gets complicated but what I want you to know in this class is the basic. Is that okay? Yes. So as your assignment, please try and understand the values. When we say 60 degrees north, what does it mean? When we say 15 degrees east, what does it mean? Are you okay? Yes, sir. So you have an assignment. Find out what the values mean, longitude and latitude values. What do they really mean? And Prince hasn't been able to join us. I haven't seen him trying to join. He's struggling. So you can teach him how to do it. Is that okay? Okay, sir. And let's have another lecture. Very likely our last but one lecture. I think on Friday. Okay? Okay. Yes, sir. All right. right. So do take care, Joe, and have a nice day.
Okay. So a question.
Okay, go ahead.
So I came across okay, I won't say it's an app, but the instant street view.
Okay.
And
Instant street. Okay, okay. I have seen it.
yes,
Okay.
yes. You know, because of the lockdown, of course we can't go out, and we are doing a design for someone at OEB. So
Okay.
we try to use instant street view to
Right.
see
To
whether
go
we
there.
can
To go
go
to the
there.
place.
Yes,
Yes,
but
yes.
it's like we got to a point and we
Couldn't get
go inside again.
better, yes.
Yes, I want to know what relation does the instant street view also have with the whole GIS?
It's very much related. In fact, the whole idea of Google Earth and everything with Google Map and Uber is GIS. So I can, if I ask you questions, my questions are going to be around Uber. I'll be asking questions on Uber, Google Earth, so that my questions will be relevant, will be current, so that you can relate. Street view is just taking pictures. Are you okay? A certain type of picture that you take, all right? And the steps are there. So you stand on the street and then you take it in a certain way, and then you upload it to Google. And then they begin, it kind of interesting, very interesting technology. And it's part of GIS, but let me just say that it's just pictures you are looking at. Are you okay? You are looking at pictures and you are being fooled. Let me just say, you are being deceived in a way to believe that you're actually walking through the streets, isn't it? Mm-hmm. So it is not your position, even as you go through the streets, you walk through the streets, you can see that your position is also recorded on a smaller map, showing that, okay, this is where you are. Okay, okay. So this is some good work that Google has done, but they have actually been to the ground to collect a lot of data. So GIS is all about data collection. If as a country you want to also build, you see, you couldn't go further because nobody has continued from there. So after COVID, after this whole lockdown thing, we should all wake up and say, the white people, they have mapped everywhere. They have done street view for every corner. And sometimes you can almost enter. In fact, I was able to enter a hotel in Germany with that. Think about it. So, but then who did that? Someone did it. But we are just here. Everybody's just chopping money, sir. It will help us. We need to get down there and work. We need to build a country, the nation, by just working. But the people are not doing it. So this one, unless you go and continue from where you got locked up.
Yeah.
But then,
it looks like it's old images quite some years back.
Yeah. But you see, the white man doesn't care anyway, because it's not his country.
Yeah.
But where if he has an interest here, he'll do it.
Okay.
Yes, if there's some gold, some oil around those areas, if you go to the mining areas where the whites are, they have serious detailed maps of the area for security reasons, for everything that they need to support their activities. Are you okay? So in fact, I learned that the whole thing behind Google mapping the whole world, like CAF campus, you can find it on Google and all that, is that they have a certain Google engine, yeah, especially for building that. And in fact, I have subscribed and they say I should wait, they'll add me to it. It's like it's a special lab where they are creating global data sets. So they don't care. They are building a data set, the whole world. But you see, if someone maps the whole world and gets to know where everything is, he can choose to show you some and keep the most to himself.
Yeah.
That is the danger for us in terms of national security. Are you okay? The security goes into all sort of areas, your food, your resources, and everything. So yeah, in these times, in fact, I actually mapped a place I did a whole mapping project at Paga. I've never been to Tamalekra before. I've never been. In fact, the person called me and he said that he want me to do this for him. And the guy in his office who's supposed to be doing this, it seems he doesn't have the ideas. Are you getting that? And I was like, don't worry, I'll do it for you. Let me charge you first. I'll take so much. I'll take, if I want to calculate it also. He said, oh, I beg you. I said, no. If he can do it, let him do it. You understand that? But then in the end, I created maps for the border between Ghana and what do you call it? Burkina Faso. There's a border post there. You could see everything. And of course, when you use GIS, you can now bring the data sets together, clean it up, and you never been to a place, but you go there. That is the power of the subject that we are learning here. And so, yeah, you were doing GIS. When you were doing that, you were doing GIS in a way you were. So it's good. That's the application. Any more? Or you good? All right, okay.
So you said you can get this recording on YouTube. I want to give it to Prince so that he can. So.
Okay, so I'm going to share the link with you when I post it.
Okay.
Yes, but then you can go to Space Infotech.
Space Infotech.
Yes, if you are subscribed, when it goes there, you get a reminder, a prompt that there's a new video. So yeah, have you subscribed?
Okay.
Have you subscribed?
Yeah, I've subscribed.
Subscribe. Okay, then in that case, you get, when I post it, you get an email.
Okay, sir.
All right. Or I'll still put the link.
Okay.
Yeah. So let's do the last topic, because I think we are all getting tired with the lecture. I get to a point where the lecture, we need to end it. The next topic is geocoding. Geocoding, you will love geocoding. Is that okay? You love geocoding. So look forward to it on Friday. You do that one. Okay, and then God willing, next week we'll do an actual practical. So that one you have to download the Quantum GIS, install it, get it ready. When we start, you have to show your screen so that I can teach you online, live, what to do. And then it's going to be fun. You're going to love it. It's good. These days, let me tell you the truth, you don't have to be stuck with one thing. You are a builder, but the more you know, the better. It gives you an advantage over your colleagues. Yeah? Okay, so Prince, Joshua, take care. Have a lovely weekend. Yeah. We are still locked down, isn't it?
No. It has been.
We cannot go wherever we want to go to.
Yeah, I still remain indoors.
That's the thing. All right. All right, you take care.
Thank you, sir. Bye, sir.